Right, so this section, the last section of this is 3.4, and it is understanding slope as a rate of change and interpreting the slope. So on page 205, it talks about the rate of change. When lines are used to model physical quantities and applications, their slopes provide important information. So slope measures the rate of change in a quantity. Okay, so rate of change is another words for slope. So let's take a look at example 7. So example 7 says the distance y in miles that an athlete training for a marathon is from home after X hours is shown in this graph right here. Find the y-intercept and what does it represent. So the y-intercept is right here at 0, 20. And what that means is at 0 time, okay, there are 20 miles away from home. It looks like that's what it says. The distance, no, yeah, from home. It's the distance there are from home. Okay, so then the graph passes through the point 1, 10. So here is 1, 10. Discuss the meaning of this point. Well, that means that after 1 hour, the runner has basically run 10 miles and is 10 miles away from home. Find the slope of this line and interpret the slope as a rate of change. So I could pick any one of these 3 points, I need 2 of them, to actually calculate the slope. But I could see just by drawing a triangle that I'm going down 20 and over 1. Down 20, I'm sorry, going down 10 over 1. Down 10 over 1. So I should get 10 as my slope. So let's take a look and see if that's what they did on the next page. So you go to the next page, and sure enough, you get a negative 10, because 10 minus 20 is negative 10, and 1 minus 0 is 1. So yeah, the slope is negative 10. So slope negative 10 means that the runner is running towards home and at 10 miles per hour. The negative slope indicates that the distance between the runner and the home is decreasing. So this is really an interesting point. So now let's take a look at average rates of change. In average rates of change, that's where we've got our graph that's not consistent. It looks like it could be a linear line, but it's kind of not exactly perfect. And so that's a lot of times we like to draw a line, a best fit that goes through this, that gives us the best slope for that. And so that's what they're talking about as an average rate of change. Okay? So in the real world, lines are often used to model data that may not be perfectly linear. In such cases, the slopes of the lines that models the situation gives an average rate of change for the quantities involved. So the example illustrates the actual number of words typed as a student writes a term paper. Because the student does not type at a constant rate, a line does not fit the situation perfectly. Okay, so that's what's going on here. So let's take a look at example 8. When a company manufactures 2,000 MP3 players, it makes a profit of $10,000. And when it manufactures 4,500 MP3 players, it profits $35,000. So we want to find the slope of the line that passes through that. So here are my 2 points. 2,000 is the players, and 10,000 is the profit. And then 4,500 is the players, and 35,000 is the profit. So we put that in our slope formula, and we get 10. Because 35,000 minus 10,000 is 25,000. 4,500 minus 2,000 is 2,500. So we get 10. So what does that mean? Interpret that. That means that when 2,000 to 4,500 MP3 players are manufactured, the profit is on average $10 per MP3 player. So for every, so he's basically making $10 profit per one player. That's how it's broken down to. So this is just nice examples of how that's done and how we use it in the real world to do that.